In this video, we're going to discuss transverse mechanical waves. You see these types of waves around you in the world all the time. But first, let's discuss the three types of waves. First, there are mechanical waves. And these can only exist within a medium, such as water, air, or even the earth, as with seismic activity. They obey Newton's laws. The second type of wave is electromagnetic. And these are light, X-rays, radar, microwave, radio, and TV. They require no medium, and in a vacuum, they travel at the speed of light, c. The third type of waves are matter waves, and these are associated with fundamental particles such as electrons and protons and quantum mechanics. Today, however, we will look at mechanical waves. As you can see from this diagram, the shape of the transverse wave is similar to simple harmonic motion, in other words, sinusoidal. In addition, any wave function that describes the movement of the wave in the string, that is the y motion, the transverse motion, is dependent on both x and t, x position and time. So we can use the equations of oscillation to describe the motion of the wave such that our wave function y of x of t is equal to y max, which is the amplitude, times the sine of kx minus omega t. And so this equation gives us our y displacement, or transverse displacement. It gives us our maximum amplitude. And this k is the wave number, not the spring constant. X would be the x position in the longitudinal direction. Omega is the angular frequency, and t is time. So this is movement in the positive x direction. If movement was in a negative x direction, our equation would become y of x of t is ym times sine kx plus omega t. Now, another type of equation that gives us a sinusoidal pattern would involve the cosine. So you could use this equation, or you could use y of x of t is ym cosine kx minus omega t. Either one would work, but we're going to stick with the sine equation for our purposes. Now let's go over some of the terms and definitions. So in that equation, ym is equal to the amplitude, which is the maximum displacement in the y direction. And that's always positive. We have kx minus omega t, and that's the phase. And this goes from +1 to -1 and back. When the phase is +1, then y simply equals ym. When the phase is -1, then y is equal to a minus ym, or y maximum. And the units for the phase are radians. You also have k, which is the wave number. And k is equal to 2 pi over lambda, which is the wavelength. And the unit for that is radians per meter. And again, this k is not the spring constant. Wavelength is the distance between the same points in a wave. For example, peak to peak. So that's one wavelength. Or it could be trough to trough. That's one wavelength. We again have our period, t, which is the time for the wave to make one full oscillation. We have omega, which is the angular frequency. And omega is equal to 2 pi over t, the period, which is equal to 2 pi f. And that is because frequency f is equal to 1 over t, or omega over 2 pi. And by the way, angular frequency is in radians per second. And frequency is number of oscillations per unit time, or hertz. And we also have our wave speed. As the wave moves along the x-axis, that has a speed v. So our wave speed, v, is equal to omega over k, which is equal to lambda over t, which is equal to lambda times frequency. And this is the speed of the wave through the medium. And I'm giving you all these values and definitions because when we do problems, we may use v in these different forms. Now, one thing to note is that if you have an equation given in the form y of x of t equals some value, let's say c times kx plus or minus omega t, this represents a traveling wave. So anytime you see an equation of this form, you know you're dealing with a traveling wave. And c could be just about any function. In our case, c is equal to the sine. Now, these diagrams show that a wave can be out of phase. So we can insert a phase constant into the wave function equation. And that'll give us a different displacement and slope of the wave at x equals 0 and t equals 0. So in this case, we're calling this x equals 0 and t equals 0. And you can see that the value of y and the slope is different. So to put that wave function in, we get y of x and t is equal to ym times sine kx minus omega t plus phi, where phi is the phase shift. And if phi is positive, the wave shifts towards negative x. And if phi is negative, the wave shifts to positive x. Now we're going to look at wave speed v on a string. And a string has to be taut or have some tension in it for a wave to propagate. So one thing we'll find is that V depends on the mass of the string, or linear density, which is mass per length, and it also depends on the elasticity of the string, or the tension in the string. And we're going to call linear density mu, and the tension in the string tau. And again, that's tension in the string, not torque. And we will find that V is equal to the square root of tau divided by mu. So this shows that in a medium, the wave speed V is dependent only on the tension and linear density of the string. A transverse wave moving down a string contains energy. Mechanical waves will transport that energy, but not mass, from one region to another. Therefore, the wave has kinetic and potential energy. Now, I drew this diagram to show that at y equals ym, or maximum amplitude, the velocity is 0, potential energy is 0, and kinetic energy is 0. And at y equals 0, velocity is at Vmax, kinetic energy is maximum, and potential energy is maximum. And this may not sound intuitive, but here's the reason why. Kinetic energy is maximum at y equals 0 because V is maximum. And its kinetic energy is 0 at y equals ym because V is 0. So that's kinetic energy. Potential energy is a little bit different. Potential energy U is maximum at y equals 0 because the string is maximally stretched. And potential energy is 0 at y equals y max because there's no stretch in the string. Now let's look at that a little closely. So if we're comparing y max versus y0, now here's the string going through that, okay? So here's y max, and looking at the reverse here of y0, and we look at dx, because dx is proportional to the stretch of the string. So if we look at a segment of string of dx, at maximum y, you see a certain segment up there. And if we look down here, this segment is actually longer than this segment. So at y max, the segment of string approximates more closely the flat string, whereas at y equals 0, the string is actually stretched more. And that's why you have these values of potential energy. It's maximum at y equals 0 because you have more stretch in the spring. That would be like a spring that is stretched a lot. Whereas at y equals 0, there's minimum or no stretch in the string. So what this tells us is we get maximum kinetic and potential energy at y equals 0, and we get no kinetic or potential energy at y equals y max. Now let's look at the average rate that energy is transported along a string. Average rate energy is transported along a string, and we would call that the change in potential energy versus time. And because these are equal, and that would be average, the change in kinetic energy versus time, average, and that becomes 1/4 mu v omega squared ym squared. And derivation of this is in the textbook. And in this case, mu is the transverse speed of the oscillation of the string element. And again, that's the element going perpendicular to the motion. And the average power that's in the string would be change in kinetic and potential energy versus time, average. And because these are equal, that would be equal to 2 times either one of them. So we'll take average kinetic energy with time. So this becomes average power is equal to, well, 2 times this becomes 1/2 mu v omega squared y max squared, which later we'll find out is equal to square root of mu times the tension times omega squared ym squared. Now I'd like to determine the wave equation. The wave equation describes the movement of waves of any type. So the wave equation that is determined by taking the first and second derivatives of our wave function y of x and t with respect to x and t. So if y of x and t is equal to ym times the sine of kx minus omega t, and we take our first and second derivatives, if we get to the second derivative, dy dx squared is equal to 1 over v squared dy squared dt squared. And in this case, we use the partial derivative because we're differentiating by both dx and dt. Now we'll look at wave interference. Two waves traveling along a string produce a resulting wave with the algebraic sum of both waves. So our resulting wave y of x and t is equal to the first wave plus the second wave. These waves combine through interference, which uses the principle of superposition to add these waves algebraically. And note that either wave does not alter the travel of the other wave. They continue to move independently. So if we actually add up these values using the wave equation, we get y prime of x of t is equal to 2ym cosine 1/2 phi times the sine of kx minus omega t plus 1/2 phi, where phi is the phase constant difference between the two waves, y1 and y2. Now, for this new or resultant wave, we note a couple things. The new phase constant is equal to 1/2 the original phase constant, and the amplitude of the new wave, y prime sub m, is equal to 2ym times the cosine of 1/2 phi. So this becomes the new y prime sub m. So if the waves are moving with a phase difference of 0, then we get y of x of t of the new resulting wave is 2ym times sine of kx minus omega t as before. And the y prime max amplitude of the new resulting wave is equal to 2 times the amplitude of the initial waves. So another way to look at this is if phi is equal to 0, then the maximum amplitude of the new wave is at its maximum point and is 2 times the amplitude of the previous waves. And therefore, these two waves have undergone fully constructive interference. If phi is equal to pi radians, or 180 degrees, which means this is 1/2 wavelength at a phase, then the amplitude of the new resultant wave is 0, and these waves have undergone fully destructive interference. And if we say that if phi is equal to 2 pi, which is 1 wavelength, or 1 lambda, then this is the same as if phi was equal to 0 and the waves are fully in phase. So in other words, if phi is any integer, so if phi is any integer number of wavelengths, now there's one wavelength, two wavelengths, three wavelengths, then that's the same as if phi is equal to 0. And one other thing, if phi is equal to 2/3 pi, 4/3 pi, etc., then if you do the actual derivation, you'll find that the maximum amplitude of the new wave is equal to the amplitude of the previous wave. Now I'd like to discuss phasors. You can use phasors to add waves together with different amplitudes. A phasor is a vector that has its tail at the origin and rotates about its tail. You can add two phasors of different magnitudes. This gives you the addition of the two waves, and you can see this in the vector diagrams I've drawn. Here you have wave y1 and wave y2 starting at the origin, and you can see here's the maximum amplitudes of those waves on the y-axis. And if we add the vectors like we do, putting the tail of y2 to the head of y1, we get our resulting vector y prime. So y2 and y1 are at a phase by the phase angle phi. And our resulting vector y1, y prime, is at a phase with y1 by the phase angle beta. And then y rotates around the origin to give us a sinusoidal pattern. Now, let's see how that works. So here's our vector y prime. And this is at time 1. We'll say t equals 0, but we'll call it time 1. Okay, if this moves here to time 2, and we plot x and y with respect to time, okay, so here's x, here's y. At time 1, or t equals 0, that's going to be at the maximum. At time 2, y is going to be less. And if we have it come out here to times 3, y is 0. If it continues, times 4, time 5, here's time 4. Times 5, it's at the minimum amount. So that would be here. So this is time 1, times 2, times 3, time 4, time 5. This would be y prime max minus y prime max. And we can keep going around the circle doing the same thing. Okay, time 5. Here's time 6, which means it starts coming up again. Time 7, this is back at y equals 0. Times 8 and times 9, it's back at y equals max. So this actually forms a sinusoidal pattern. And this is how a phasor moving around the origin will produce a sinusoidal wave based on time. And in this case, the wave equation becomes y prime of x and t is equal to y prime max times the sine of kx minus omega t plus beta. Okay, so this is the amplitude of the resulting wave, and that's the phase constant between y prime and y1. So this is how we use phasors to add waves of different amplitudes. Now I'd like to go over standing waves. A standing wave forms when two waves of the same amplitude and wavelength move in opposite directions and interfere with each other. The resulting wave shape or pattern does not move either left or right, and the maximum and minimum points do not change. So in other words, a standing wave, you would have one wave moving like this, x and y, and another wave moving like this, and these waves don't go left or right. They just stand like that. And these minimum points never move. They remain the same. And those points are nodes. Those are minimum points in a standing wave. And these maximum points, okay, these are antinodes. And they're the maximum points in a wave. Now, it turns out the equation for a standing wave is y prime of x of t is equal to 2 times y maximum sine kx times cosine omega t. And this becomes the amplitude at x. And the maximum is 2ym. Again, I'd like to point out that we've been using the sine function. You can also use the cosine function in a wave equation, and this would come out to be 2ym sine kx times sine omega t. But we've been using the sine function, so we'll stick with this form of the equation. In a standing wave, the amplitude of the standing wave varies with x. And the amplitude of a standing wave equals 0 whenever the sine of kx is equal to 0. And that occurs when kx is any integer number of pi, or half a wavelength. And to go back up to the diagram, you have a node at every half wavelength. So that would mean that x is equal to n times pi over k. So this gives us the position of the nodes where the amplitude is 0. So x equals n times pi over k, which, if we look back at our derivations, that's equal to n times lambda over 2, where n is equal to 1, 2, 3. So this gives us the position of the nodes. Now, on the other hand, the amplitude is maximum, which is 2 times ym, where the value of sine kx is equal to 1. And this would give us kx is equal to pi over 2, 3 pi over 2, etc. Or kx is equal to n plus 1/2 pi. Or x is equal to n plus 1/2 pi over k. So that's the position of antinodes. So here's our position of our nodes. Here's our position of our antinodes. And since k is equal to 2 pi over wavelength, this also becomes x is equal to n plus 1/2 times lambda over 2, where n is equal to 1, 2, 3, etc. These are just another way of finding position of antinodes. The next thing I want to go over is boundary reflections. So a wave on a string can reflect off a boundary in 2 ways. First, if we have the wave traveling down a string and it hits a boundary that's fixed, it'll reflect and bounce off that boundary, and it actually reverses. And this is called a hard reflection, where one end is fixed and the boundary can't move. And you always have a node here because, again, that is not moving, and that's the minimum value. So there must be a node at the boundary, and the reflected wave cancels the initial wave. So you get destructive interference. So this is the first way. The second way is you have a wave coming to a boundary, and in this case, let's assume we have a ring that can float up and down on that boundary. Well, okay, so that's going that way, that's going that way. This reflects in a way where you get constructive interference. So here the boundary can move, and it moves up and down perpendicular to the wave, which is moving in that direction. So here you have an antinode, because you get an amplitude. The reflected amplitude is 2 times the initial amplitude, and this is called a soft reflection. And this is the second way a wave can reflect. And again, as this wave comes in and reflects, the reflected peak matches the incoming peak, and gives you twice the amplitude. In a hard reflection, the reflected peak is the opposite of the incoming peak and gives you destructive interference. Let's talk about resonance. For a string fixed at both ends, for example, a guitar string or piano string, a wave that reflects back and forth can result in many overlapping waves that interfere with each other. At certain frequencies, you can get a standing wave with nodes and antinodes. This is resonance at these resonant frequencies. And a standing wave must have a node at each end. So you can see from this diagram, you have a standing wave fixed between 2 points, and the dots are the nodes at each end, and the x's are the antinodes, which are the maximum amplitude. And it has a length between the nodes is L. But note that in this case, L is equal to 1/2 of a full wavelength, or a wavelength is equal to 2L. So a standing wave can be set up on a string of length L by a wave with a wavelength equal to 2L over N, where N is 1, 2, or 3, etc. So if N is 1, then the wavelength, as in this case, would be 2 times L. If N is 2, then this is actually 1 wavelength, because you're going from the same point to the same point, and so on. And since frequency is equal to wave speed over wavelength, we get then that the resonant frequencies, f of n, is equal to n times v over 2L, where n is 1, 2, 3. So this gives you your resonant frequencies of a string. And it turns out that this gives you all possible frequencies that that string could have. Now, since the wave speed is equal to string tension over its density, this becomes n over 2L times the square root of tension over linear density of the string. So again, tau is the tension in the string, and mu is the linear density. And in this case, n is equal to the harmonic number. So let's go back to our frequency is equal to NV over 2L. So the lowest frequency is when n equals 1. So F1 is equal to V over 2L. And this is called your fundamental frequency, or first harmonic. Now, what happens when n equals 2? Then you get F2, which is 2V over 2L. And this is called the first overtone. or second harmonic. And if n is equal to 3, then F3 is equal to 3V over 2L. And this is your second overtone or third harmonic. So that's for that, that's for that, and that's for that. Now, the resonance we've talked about is for one dimension, in other words, a string. But you can have resonance in 2 dimensions, such as a kettle drum, or even 3 dimensions, such as the swaying of a building in wind. And now we're ready to do some problems. Here's our first problem. A wave on a string can be described by the equation y of x and t equals 0.28 times sine 12x minus 400t in millimeters, where x is in meters and t is in seconds. What is the transverse velocity and transverse acceleration of the string segment at x equals 20 centimeters? What is the displacement at this point if t equals 3 seconds? So we're given y of x and t is equal to 0.28 times sine of 12x minus 400t. And we're given x is 20 centimeters, but that needs to be in meters. That's equal to 0.2 meters. So the transverse velocity is equal to the derivative of y with respect to t, which becomes 0.28 times minus 400 cosine of 12x, which is 0.2, minus 400t, and that becomes millimeters per second, or that's equal to 112 minus 112 times the cosine of 2.4 minus 400t, which is minus 0.112 times the cosine of 2.4 minus 400t in meters per second. So this is our transverse velocity. Now we want to find acceleration. Transverse acceleration is the derivative of the velocity with respect to t, which becomes minus 0.112 times 400 times the sine of 2.4 minus 400t in meters per second squared, which is equal to minus 44.8 times the sine of 2.4 minus 400t in meters per second squared. So this is our transverse velocity and a transverse acceleration. Now we want to know what the displacement is, or y, at x equals 20 centimeters and t equals 3 seconds. So we plug that into our equation. We get y of 0.2 meters in 3 seconds is equal to 0.28 times the sine of 12 times 0.2 minus 400 times 3 seconds, which is equal to 0.28 times the sine of 2.4 minus 1200, which is equal to 0.28 times the sine of a minus 1197.6 millimeters. Now, that is actually in radians, and we want to convert that into degrees. So we have minus 1197.6 rads, and there are 2 pi rads in 1 revolution about the axis. So this becomes a minus 190.7 revolutions or cycles. But every revolution brings us back to the same point. So we can get rid of all of the unit numbers of revolutions, the 190, and just focus on the 0.7 revolutions. So a minus 0.7 revolutions or cycles times 360 degrees per revolution gives us a minus 252 degrees. And that's the same as a positive 108 degrees. So going back to our equation up here, y equals 0.28 times the sine of 108 degrees, which is equal to 0.28 times 0.95, which equals 0.27 millimeters. So that's our displacement at 0.2 meters in 3 seconds. Here's another problem. A wave has the function y equals y sub m times the square root of x plus vt. Show that this function satisfies the wave equation. So, first of all, the wave equation is second derivative of y with respect to x is equal to 1 over v squared times the second derivative of y with respect to t. So we have to take our first and second derivatives of y equals ym times x plus vt to the 1/2 power. So let's do the derivative with respect to x. So dy dx is equal to y sub m over 2 times the square root of x plus vt. And the second derivative of y with respect to x then becomes y sub m over 4 times the square root of x plus vt to the 3/2 power. Now let's take the derivative with respect to t. So dy dt is equal to ym times v over 2 times the square root of x minus vt. And the second derivative of y with respect to t is equal to y sub m over 4 times v squared over the square root of x plus vt to the 3/2 power. So when we look at this expression and this expression, we see that second derivative of y with respect to x is equal to the second derivative of y with respect to t if we divide this by v squared. So that's how we get these to be equal, which does satisfy our wave equation, as you see up here. Okay, Here's a problem where we're going to use phasors to solve it. Two transverse traveling waves with the same frequency are traveling in the same direction and combine. If their amplitudes are 8 and 10 centimeters and have a phase difference of pi over 2, what is the amplitude of the resulting wave? What is the phase shift of the resulting wave? Use phasors to solve this problem. So if we use phasors, what we do is we lay out our vectors. So if one vector is 1, 2, 3, 4, 5, 6, 7, 8, okay, we'll call this wave y1, and another one is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, but now look, it says the phase difference is pi over 2. So pi over 2 is equal to 90 degrees. So the two waves are 90 degrees. So actually, wave 2 would be up here, okay, tail to tail, where this is x and this is y. So the next step would be to put them head to tail. So if this is wave 1 and this is wave 2 that are phase shifted by pi over 2, our resulting vector is shown like that. We'll call that y prime. And we'll call this angle beta, which is the new phase shift. So we know that y prime is equal to the square root of y1 squared plus y2 squared, because this is a right triangle here. So that's equal to the square root of 8 squared, which is 64, plus 10 squared, which is 100, which is the square root of 164, or y prime is equal to 12.8 centimeters. And we want to know what the new phase shift is of the resulting wave. Well, we know that the tan of beta is equal to y2 over y1, which is equal to 10 over 8, which is equal to 1.25. So the arctan of 1.25 is equal to 51.3 degrees. So beta is equal to 51.3 degrees, the new phase shift. Our next problem involves wave interference. A wave is traveling in the plus x direction. It interferes with another wave traveling in the same direction with the same amplitude, frequency, and wave number, but a phase difference of phi. If each wave has an amplitude of 8 centimeters and their phase difference is pi over 2, what is the amplitude of the resulting wave? If the resulting amplitude was 8 centimeters, what would be the phase difference in this case? So let's look at our two waves. We'll call wave 1. We'll describe that as equal to y of m1 times the sine of kx minus omega t. And we'll say wave 2 is equal to ym2 times the sine of kx minus omega t plus a phase difference of phi. And we're given that maximum y of 1 is equal to ym of 2, which is equal to 8 centimeters. And we know that the wave equation with wave interference is given by y prime is equal to 2 times y max times the cosine of 1/2 phi times the sine of kx minus omega t plus 1/2 phi. So this is the wave equation of our new wave due to the interference of y1 and y2. Well, it turns out that this is the amplitude of the new wave. So that's the actual amplitude of y prime. And this is the other part of the wave equation. So to find the amplitude of our new wave, which the problem asks, we say that y prime m is equal to 2 times ym, which is given as 8 centimeters, times the cosine of 1/2 phi. And phi is given as pi over 2. So the amplitude of the new wave is equal to 2 times 8 times the cosine of pi over 4, which is equal to 16 times cosine. Pi over 4 is the cosine of 45 degrees, which is equal to 16 times 0.71, or the amplitude of the new wave due to interference is equal to 11.3 centimeters. Now, the question asks, if the resulting amplitude was 8 centimeters, what would be the phase difference in that case? So we're saying that if the resultant amplitude turned out to be 8 centimeters, what would phi have to be? So again, in this case, we say that this term, 2 times ym times the cosine of 1/2 phi, in this case, would be 8 centimeters. So we get that the cosine of 1/2 phi would be equal to 8 over 2 times y sub m, which is equal to 8 over 2, and we're given y sub m is equal to 8. So that becomes 1/2. So we know that the cosine of pi over 3 is equal to 1/2. Therefore, 1/2 phi must be equal to pi over 3, or phi is equal to 2 pi over 3. That's what the phase difference would have to be to give us an amplitude of 8. This next problem states, the wave shown is traveling at 24 meters per second. What is its frequency and wavelength? Describe the equation for this wave in the plus x direction. If the string's linear density is equal to 0.3 grams per meter, what is the average energy per time transported down the string? In other words, power. So this is actually x, this is y. So the equation for this wave in the x direction would be y of x and t is equal to y sub m times the sine of kx minus omega t. So we'd have to find most of these values in this equation anyway. So the first thing to notice is that there are 5 half wavelengths in 20 centimeters. So there are 5 half wavelengths, gives 20 centimeters. So our wavelength comes out to be 8 centimeters. We also see from the graph that our amplitude, or ym, is equal to 8 centimeters. And now we just have to find k and omega. So we know frequency is equal to velocity over wavelength. And we're given our velocity is equal to 24 meters per second in the problem. So, so that's equal to 2,400 centimeters over 8 centimeters. We have to keep our units the same. So our frequency is actually 300 hertz. And then our angular frequency is equal to 2 pi times frequency, which in this case comes out to be 1884 radians per second. And our wave number k is equal to 2 pi over lambda, which is equal to 0.8 centimeters. Okay, so our wave equation becomes y of x and t is equal to ym, which is 8 centimeters, times the sine of k, which is 0.8 x, minus omega, which is 1884 t. So that's the wave equation for this wave. What is the power transported down the string? So we know our power equation, the average power is equal to 1/2 linear density times velocity times angular frequency squared times amplitude squared. So let's plug in these values. It's 1/2 times the linear density, which is 0.3 times 10 to the minus 3 kilograms per meter, times speed is 24 meters per second, times angular frequency is 1.88 times 10 to the third squared, times amplitude, which is 0.08 meters squared. And if you go through the math, you get the average power comes out to be 80.6 watts. Our next question states, an open cello string is 80 centimeters long and is playing a note of frequency 440 hertz. Where must the musician compress the string with a finger to produce a note of 660 hertz? So we have a string that has a note playing at 440 hertz and it's 80 centimeters long. Now this is the fundamental frequency, which as you can see is half a wavelength. So if L is 80 centimeters, okay, L is equal to 1/2 a wavelength, which means that our wavelength is actually equal to 1.6 meters long. And we're given that this fundamental frequency is 440 hertz. So the first thing we need to do is find the velocity of the wave on that string, and that's equal to lambda times frequency, which is equal to 1.6 times 440, which gives us 704 meters per second. And we want to find the velocity because that remains constant as you compress the string with your finger. So now we want to know for a frequency of 660 hertz, what would be the new wavelength or fundamental frequency. So the velocity is the same. That's equal to our new wavelength times 660 hertz using this formula. So lambda would become 1.1 meters. So we'd have to compress the string from 1.6 to 1.1 meter to get to this new frequency. So we need to remember that that 1.1 meter is a whole wavelength. And again, we're looking at a fundamental frequency, which is half a wavelength. So we need half of that, or 1/2 times 1.1 meter. So that would mean that would be at 55 centimeters. So the player needs to take a string that was originally 80 centimeters long and compress it down to 55 centimeters to go from 440 hertz to 660 hertz. The main thing to note here is that when we talk about fundamental frequencies, we're talking about half a wavelength. So remember that. Here's our last problem. The third harmonic is playing on a string 3 meters in length. What are the positions of the nodes and antinodes? So a third harmonic is the second overtone, and we're looking at a wave with 3 half wavelengths. Okay, so we have 4 nodes. 1, 2, 3, 4. And the string is 3 meters in length. So we can divide these up and see that our nodes are at 0, 1, 2, and 3 meters. And our antinodes are halfway between them. So here, here, and here. So that would be at 0.5, 1.5, and 2.5 meters. So that's where the nodes and antinodes are.